Boom, ice table, right? So here's our setup. We have 100 milliliters of 0.7 molar acetic acid, right? We have 5 milliliters of 1.5 molar sodium hydroxide, and we know what the reaction is going to be. Notice that all of our coefficients here, our stoichiometric coefficients, are all 1, because this is just an acid-base reaction. I guess technically we have water in here too, but nobody cares about water. So the ice table, what are our initial concentrations? Well, our initial concentrations are of course given right here. We're going to convert everything to moles so that we don't have to worry about the ever-changing volume of this reaction, right? If we add 100 plus 5, we have 105. We don't want to divide everything by 105, so we're just going to go to moles. So I'm going to take 0.1 liters times 0.7 molar, and that's going to give me 0.07 moles of acetic acid to begin. Right, so this is my initial concentration of acetic acid. For sodium hydroxide, we're going to take 0.005 liters times 1.5 molar, and liters times moles per liter is going to give me moles, and the number of moles is going to be 0.0075 moles. The initial amount of conjugate base is 0 because we haven't produced any when the reaction starts. Now, what we know, how do we fill in the rest of this table, right? What we know is that the equilibrium lies very strongly toward the products in this, right? And so we're going to assume that the equilibrium lies completely toward the products in that, right, all of the sodium hydroxide will react to create conjugate base. And so the sodium hydroxide that reacts is going to be all of it. So the change is going to be minus 0.0075 moles, which gives us 0 sodium hydroxide once this reaction has reached equilibrium, right? This is the idea that this is a strong base. This is what we define a strong base as. Strong bases do not stick around in reactions. They react and produce products, right? So anytime you have a strong base, this is why we use strong bases for titration. It makes this calculation so much easier. So now, once we know one of these change values, we can figure out the others because they all have the same stoichiometric coefficient. That means that the products will go up by the same amount that the reactants go down. Right? And then we can fill in this here. So this comes out to be 0.0625 moles of acetic acid. And of course over here we just have 0.0075 moles of conjugate base. Hopefully that all makes sense, right? So we figure this number out right in the middle because we know that all the sodium hydroxide reacts. And so we have to get to 0 here. Once we know this number, we fill in that number for the other changes, and we just do our simple addition and subtraction to get us there. Now, what we have is we have a concentration of acid, a concentration of its conjugate base, and we have a pKa because we know that the pKa of acetic acid is 4.74. So this is of course set up for the Henderson-Hasselbach equation, which takes too long to write. pH equals pKa plus the log of base over acid. So plug everything in. The nice thing is that all the numbers that we know are on the right side of the equation. So this is really just plugging numbers in and evaluating this. So the base is 0.0075. The acid is 0.0625. And then we calculate this all out. So these two divided by each other equals 0.12, 4.74 plus log of 0.12. Plug that into your calculator and you get a pH of 3.82. So once again, what we see is our initial pH was 2.44. We've added 5 mils of 1.5 molar NaOH, and we've gotten up to a pH of 3.82. So far, this is kind of how we are going to track the pH through these equations, right? The more base we add, we create a buffer. Of course, there's a couple of points that I want to draw your attention to, right? And I think that these points will not surprise you, right? The first one is what happens when we get to the point where the amount of acid and the amount of base are equivalent to each other, right? So we can keep going. So for now, I don't know, we'll come back and draw a titration curve in a minute. But let's say that we get to a point where we have the amount of sodium hydroxide is now, so we're at 0.7 molar times 100 milliliters, and this was 0.07 moles. Right? So we're going to add, so at some point we'll have added 0.035 moles of sodium hydroxide. Right? And when this happens, this means that this will convert to 0.035 moles of conjugate base, right? This is, I'm doing an ice table, but not drawing out the ice table, but this would be the same thing, right? If we have added 0.035 moles of sodium hydroxide, we have to get to 0. So we know that the change will be negative 0.035. So it would be positive 0.035, negative 0.035. So once we've added that much, we are going to have equivalent concentrations of conjugate base and acetic acid. Right? And of course, at this point, we plug it into the Henderson-Hasselbach equation. 4.74 is our pKa plus the log of 0.035 divided by 0.035. This turns into the log of 1. The log of 1 is 0. So we get 4.74 plus 0. And so the pH at this point equals 4.74. Right? So there is a point in the titration where the concentration of acid equals the concentration of base. At that point, and at that point, the pH equals the pKa of the acid. So this is kind of good to know as we do these titrations, as we kind of add more and more base, there is a point in every one of these titrations where we can find the pKa of our acid because we know that when those concentrations are equal to each other, the Henderson-Hasselbach equation, those terms drop out, the log of the base over acid becomes 0, and we get the pH equal to the pKa, which is kind of cool, right? Furthermore, we know that this is halfway between, like the amount of sodium hydroxide we've added is half of the amount of acid that's there, right? So there's a point in titration where, and this occurs, come on, give me more marker. It's not gonna do it, right? I'm gonna put a star on this. This occurs when the amount of strong base added is half of the amount of weak acid. Which kind of makes sense. This kind of all falls out of the Henderson-Hasselbach equation, right? If we set this up so that these two numbers are equal, then the pH will equal the pKa. That's just what the Henderson-Hasselbach equation means, right? So this is, of course, the best buffer, the most buffered point in this titration is when these two numbers are equal and the pH equals the pKa. And the way we get there is we add half as much sodium hydroxide as we have weak acid. All right, there's one more thing I got to tell you about strong weak acids and strong bases. I'm going to again bump that to the next video because this just keeps going, right? But we're up to 10 minutes already on this video, and I'm sure that your eyes are glazing over, and this is all. I mean, sorry, you're probably on the edge of your seat. Can't wait to watch the next video. So the next video is coming. Hang in there. It'll be here soon.